So we're going to hear from Sara Goeking. Her research focuses on developing methods for comparing historical and recent forest inventory data sets, mapping trees in non-forested areas, assessing whitebark pine distributions in mixed species stands, and applying robust forest modeling techniques in developing countries. Today, she'll talk to us about integrated analysis data. Sara.
Thank you, Eric, and thanks everyone for sticking around for the very end, the very last session here. Before I begin, I would like to acknowledge my co-authors who are all with Rocky Mountain Research Station, and I would especially like to thank the dozens, if not hundreds of field staff that work really hard every day to collect field data for projects like this one. So we began this project with some pretty broad objectives, broad scales and broad focus. We wanted to characterize burned areas, post-fire conditions over time, and fire severity classes relative to pre-fire conditions, and also percent tree mortality due to fire. And when I say tree mortality, we actually use percent reduction in live basal area due to fire. So we're doing this at very broad scales using two long-term landscape level data sets. First, the Forest Inventory and Analysis, or FIA data set, and second, the Monitoring Trends in Burn Severity, or MTBS data set. I'm going to talk a little bit first about both of these data sets, and if you do anything with spatial data or intensive plot data, these are both data sets that you might find useful. And they're both publicly available. So first, the FIA program is an ongoing nationwide forest monitoring program conducted by the U.S. Forest Service. It uses nationally consistent methods and a nationally consistent sample design. Even though it's nationwide, it's administered by 4 different regions, and I work with the 8 interior western states shown on this map, including Utah and 7 other states. And the website shown here is where you can download the data. And I'll show this again on my final slide, so if you're really curious, you can copy it down then. There we go. Okay, the FIA sample is considered to be a spatially and temporally balanced plot network. We have a plot about every 6,000 acres. The map on the left there has kind of a chicken wire mesh overlaid on the Northern Rockies. Each one of those hexagonal polygons has a plot, so the plots are each about 3 miles apart. And in the western US, it takes 10 years to measure all of those plots. We do 10% of the sample each year, and rather than doing 10% here and then 10% here and then 10% here, we have what we call spatially interpenetrating temporal panels or samples. And these plots sample all forest types. We also have plots on non-forest lands, but we sort of begin the sample by saying, is it forest or non-forest? We sample all land ownerships, including federal lands, state and local government, private lands, and tribal lands, as long as we get permission from the owners or managers to access the locations. So in the 8-state study area that we did the study on, we have about 93,000 plots, and about 35,000 of those are forested. So each year, we're collecting data from about 3,500 forest plots. And when I say forest land, FIA defines forest land as any land that's at least a certain width, a certain size, that either has 10% tree cover or formerly did in the past. And that's important when we talk about fire, because say you have a dense stand of trees that's either clear-cut or experiences stand replacing fire, the fact that there's no tree canopy cover there doesn't make it non-forest according to the FIA definition. We want to continue monitoring that site as it recovers from that disturbance. This is what an FIA plot looks like. It covers about an acre on the ground and consists of 4 subplots, each of about a 7-meter radius. At the plot level, we summarize carbon and biomass data, tree growth and mortality, downwoody materials, and then some understory vegetation information, some soils information, noxious weeds where they occur, and a few other variables. On each of our 4 subplots, we also have what we call microplots, where we measure regeneration. So we're looking at seedlings and saplings. And here you can see in the tree data the size categories that we use to distinguish trees, seedlings, and saplings. Okay, now I'm going to talk about our other data set, the MTBS data set. This is a collaborative project between the U.S. Forest Service Remote Sensing Application Center and also the U.S. Geological Survey. MTBS maps all large fires going back to 1984 and through the present. They're continually updating and also refining their algorithms. When they say large fires are considered to be those that are at least 1,000 acres in size in the western U.S. and 500 acres in the east. Like the FIA data set, the MTBS data are freely available for download at mtbs.gov. So someone asked yesterday whether these fire severity classes are based on some threshold for tree mortality. They're not. And so one of the objectives of this project was to see whether those severity classes actually do correspond well to percent mortality caused by fire. The way that the MTBS layers are developed is by looking at pre-fire and post-fire Landsat imagery, specific bands, and taking the difference between those spectral signatures. First, they simply delineate the burned area perimeter. So that's polygon or vector data. That's one data set. The second data set is a raster, a set of rasters representing fire severity. So they classify the differences of these Landsat scenes into this numerically continuous burn severity index and then categorize that index into these 6 classes that you see here. The 2 lowest classes, the 2 lowest on the list are increased greenness, which is primarily applicable in non-forest areas, so non-treed areas, and then non-mappable area. We didn't consider those in our analysis. We just looked at the first 4 classes, so 1, which is unburned or very low severity, 2, which is low, 3 is moderate, and 4 is high severity. So this is, in yellow, you can see our 8-state study area. This is 10% of our sample. This is 1 year's worth of FIA plots, and if I showed you all of them, it would look like a big green blob. So lots of plots. This is the distribution of all fires in the MTBS data set from 1984 to 2012, which was all that was completed when we began this project. That was just over 6,000 fire perimeters within our 8 states. So here you see both the fire perimeters and the plots, and then on the left, that pie chart just shows the proportional distribution by area of major forest type groups within our 8 interior western states. So the most common ones are ponderosa pine, Douglas fir, pinyon juniper woodlands, and lodgepole pine forests. Other is actually, that can be broken into almost a dozen other types that occur in much smaller proportions. So we had some specific questions that we wanted to ask by relating these 2 data sets, and depending on the question, we wanted to use slightly different sets of FIA plots to answer those. First, we wanted to estimate the percent forest and non-forest within burned areas. Usually, when you see estimates of fire acreage, there's no mention of what the cover type is except to say, well, it's burning primarily in sagebrush. But there's usually not a quantitative assessment of how much of it might be forest or other cover types. So first we want to try to estimate the proportion of forest and non-forest. We had about 6,300 plots for that particular analysis. Second, we wanted to characterize forest type groups in burned areas. For that part of the analysis, we used all forest plots, both pre-fire and post-fire, within MTBS fire perimeters. That was about 3,200 plots. Third, we wanted to characterize post-fire basal area, live basal area, and also density, specifically seedling and sapling density, to look at regeneration. So for that analysis, we just used post-fire plots within fire perimeters. That was over 2,300 plots. And finally, to test the MTBS severity classes relative to initial conditions and also percent tree mortality, we wanted to have both a pre-fire and a post-fire measurement of the same plot to do that analysis. So we actually dug further back into the historical forest inventory data just to have a bigger sample, and we had 735 of those plots. In terms of the spatial analysis, we intersected the plots with first the vector data, the burned area perimeters, and then second with the severity rasters. So if you go to mtbs.gov and you want to access the severity data, there's one raster for each year of fires. And what we did was we first collapsed or condensed all the years of fire severity into one sort of concatenated raster so that we could efficiently intersect that with our plot data. Then we identified plots that were measured both before a fire and after a fire. And then extracted the most severe severity code of any fire that occurred between measurements. And that was kind of important because there were many plots that burned more than once. So what we learned first in terms of burned area characteristics, since 1984, across these 8 western states, about 41% of the burned area was on forest land. That varied quite a bit spatially, from 10% in Nevada to about 65% in Montana. And the two fires that you see on the right, the Milford Flat and Twitchell Canyon fires, sort of represent two opposites of the spectrum, the Milford Flat being almost no forest and Twitchell Canyon having quite a bit of forest land within the fire perimeter. These 4 forest types, ponderosa pine, pinyon juniper, Douglas fir, and lodgepole pine, were the most commonly burned. Again, those are the most common ones in our 8 states. However, their proportion within the burned areas was not completely comparable to their proportion across the landscape in general. So in general, the ponderosa pine, Douglas fir, and lodgepole pine burned in greater proportion than you might expect based on their distribution across the landscape. And for pinyon juniper, the opposite was true. If we looked at time since fire, this is just a histogram, number of plots by number of years since fire. We found that about 2/3 of the plots had burned less than 10 years prior to measurement, so kind of reflecting something that we've heard again and again about increasing fire acreage. This histogram shows number of plots by post-fire live basal area category. And about 1/3 of all of our post-fire plots had no residual live basal area. I should note here that most of the tree species and forest types we're looking at are not capable of regenerating and growing trees large enough to contribute to live basal area during the duration of our study. So when we're showing post-fire live basal area, we can pretty safely assume that that is all residual survivor trees contributing to that live basal area. Next, we wanted to look at post-fire recovery. So how are live and dead basal area and then seedling and sapling density changing with time since fire? So on the x-axis here, we have time since fire in 5-year categories. On the far left, we have pre-fire or not yet burned plots just for comparison purposes. The green bars show live basal area, and we can see that it dropped by more than half immediately post-fire on average. Also, all the error bars that I'm showing are plus and minus 1 standard error of the mean response. Immediately post-fire to 25 to 30 years post-fire, we saw a slight decrease in live basal area, which we're pretty sure that's just background mortality of those survivor trees. Now, if we look at the red bars, dead basal area on immediate post-fire plots was about 3 times that on unburned plots, and it decreased steadily to 25 to 30 years post-fire, and at that point, dead basal area was just under half what it was immediately post-fire. So that tells us that there's a half-life of about 25 years for these post-fire snags. If you're familiar with the program FVS, the Forest Vegetation Simulator, that typically assumes that when a tree dies, it's down within 10 years. And so this shows that, maybe that needs to be revisited. Okay, so finally, we're looking at the fire severity class. This is really the meat of what we wanted to know, is how informative are those MTBS fire severity classes. First, we look at initial conditions, so pre-fire conditions. And we found that the highest severity class, class 4, was definitely correlated with high initial total and live basal area. So that shouldn't really be a surprise. But it just verifies what that high severity class in the MTBS dataset is telling us. Next, we looked at these severity classes by forest type group. First, if you look at the bottom row, all forest type groups together, we see that the distribution of our plots among these severity classes is about equal, from 22% to 31%. And as I mentioned earlier, some forest types burned in greater proportion than you might expect based on their occurrence across the landscape. Some also burned at higher severity than you might expect. Those are fir spruce and lodgepole pine, and then the pinyon juniper and ponderosa pine tended to burn less in that highest severity class relative to the other forest types. Okay, so finally, what is the percent mortality that corresponds to each of these 4 severity classes? The black bars here are all forest type groups lumped together, and we did find that there were definitely significant differences among the 4 severity classes. Where we had the first severity class, the average was 5 to 10% reduction in live basal area. The low, or class 2 severity class, was about 15%. 25%. Class 3 was about 70%, and then class 4, the highest severity, was generally over 80%. So still not 100% mortality, but quite high. And that pattern held true for most forest type groups. Lodgepole pine kind of bucked that trend a little bit, but that also was the forest type group with the smallest number of plots in this analysis. So in terms of management implications, I think that this shows, though, that if you want to rely on the MTBS severity classes to get an idea what they mean in terms of percent mortality, at least at a very broad scale, that's probably a safe thing to do. And so what we need to do next is see whether these severity classes also correspond to changes in understory vegetation and downwoody materials, and then start looking at smaller scales, both in terms of the individual forest types and also, say, individual forests or BLM districts, to see whether we can estimate what the percent mortality would be, and maybe put confidence intervals on those that might be useful for managers. So to summarize, what we learned in terms of burned area characteristics is that first, About 40% of all the burned areas, at least of the large fires since 1984, burned on forest land. The representation of forest type groups that burned was not equivalent to their distribution across the entire landscape. In terms of post-fire recovery, about 1/3 of post-fire plots experienced stand replacing fire and had no residual live basal area. Mean post-fire dead basal area was about 3 times what it was on unburned plots, and those snags had a half-life of about 25 years. That 25 to 30 year time frame that we were looking at was long enough post-fire to capture the peak of seedling recruitment and then the decline, but not long enough to capture the peak of sapling recruitment. In terms of fire severity, we found that high fire severity is definitely related to initial live and total basal area. And again, when I say high fire severity, I mean as represented in the MTBS data set. So again, trying to validate those classes. High fire severity also occurred disproportionately in some forest types and not in others. And then again, to summarize what those severity classes mean in terms of the percent basal area killed, you can see here ranging from under 10% for class 1, which varied widely. Class 2 also varied widely. And then classes 3 and 4 were a lot more consistent among forest type groups and had smaller errors on those as well. So before I take questions, actually, I'm going to go through some pictures really quickly. I think pictures worth 1,000 words. So here are some photos of plots. Our crews take photos on every plot in the 4 cardinal directions. This is a plot that burned in 2002 in Colorado. It was measured in 2008. All the photos are from 2008, and this is a plot that experienced a type change from coniferous forest to aspen and had dense aspen regeneration 6 years after the fire when it was measured. So here's a plot that burned in fairly early 2003. It was measured later that same year. And then the same plot on the right 10 years later in 2013. And this also experienced a type change post-fire. It was initially classified as white fir. 10 years later was classified as having 2 separate forest types, Douglas fir and aspen. This is the 1999 Anaconda Fire in Montana, measured in 2003 and again in 2013. It was lodgepole pine, and as you can see, it was nearly 100% mortality. Actually, it was 100% mortality, and then had dense regeneration. And in our second measurement, 14 years post-fire, we had similar densities of seedlings and saplings. This is the Limington Complex here in Utah that burned in 1996, measured 7 years post-fire and again 10 years after that. The crew did record cheatgrass on the plot in 2003, 5% cover on 2 of our 4 subplots, and none in 2013. And then finally, this is the 1988 Storm Creek Fire in Montana, measured 15 years post-fire in a white bark pine forest type, and again 10 years after that. There was no live white bark tallied until the crew went back in 2013 and started tallying seedlings and made this note here, very little regeneration on the acre, but white bark pine seedlings are coming in. So we'll see what happens in 2023 when they go back. So with that, thanks for your attention. I'd be happy to answer any questions.
We've got a few minutes for questions. Sara?
Yeah.
Do you have any feel for the half-life said 25 in general, but multiple really different features.
Yes, it is. That's a good question, and we haven't looked at that, but we would love to. And since you've asked that question, and we haven't looked at that yet, I would just like to say to you and anybody else that a lot of times what we look at specifically is driven by what FIA customers want to know. And so that's something that we definitely could look at.
I want to look at
Okay.
I also would like to. Terry, is this published?
It's in review. John Shaw is the lead author, and then the other three of us are on it as well. Journal of Forestry.
So what percentage of our forests have burned overall?
I should know this, but I don't. Since 1984. Justin, do you happen to know? Okay, sorry, the question was what percentage of our forests have burned. I know that since 1984, the total acreage of those fires was about 50 million acres. That's the sum of all the fires. And if you do a spatial intersection of those and don't double count places that burned more than once, it's about 42 million. So of the areas that burned, about 20% of them burned more than once since 1984. Doesn't answer your question, but okay. I'll look into that.
Any other questions for Sara?
Any others?
All right, thanks.
Thank you.